Oh, yeah. Thank you.
I would have given it to Mike yesterday, but I didn't go.
Huh?
I would have given it to Mike yesterday.
Oh, that's fine. I appreciate it. Thank you.
Come on. There it goes. She fell asleep.
That's pretty good.
All right, let's go ahead and get started and start kind of warming up. So you can kind of look at these problems, so going over chapter 6. But let's do a few announcements. So I forgot to make some announcements. So next week, if you've looked at the calendar, so next Tuesday is a holiday. So it's Veterans Day. So a little unusual to have a Tuesday holiday. So we won't have class that day. And then if you've looked at the syllabus, right, there's going to be no lab next week because of that. But then that means that Thursday is an excellent day for makeup. So a lot of people have been absent and for different reasons. So that Thursday then is a great makeup day. So if you need to make up something, let's plan for that Thursday, and you can email me so we can have the stockroom get some setups going. So that being said, we'll kind of see how far we get with Chapter 7 today, and then if you look at the syllabus, we're going to be doing Chapter 7 and 10 next week. Just kind of building upon each other, so looking at these molecules and kind of building geometry and looking at their shapes. So hopefully the one day won't hurt us too badly. And we probably won't have a quiz next Thursday, I would say. Or if we do, it'll be like a take-home quiz because of that, since we want to maximize lecture time next week. Okay, questions about the holiday and then labs, schedule, or anything? Yeah. We'll have a quiz this week. Well, actually, we'll have a quiz, but I'll explain it once we get there. It's going to be a group quiz today because it's going to be over like the material in the week that I wasn't here. So just trying to like catch everybody up, make sure we're on the same page with our group quiz. But like I said, I'll explain that. But yeah, we'll still have a quiz today, but group quiz. And on that note, so I did grade your midterms. So the average was a 65%, and so that's as a percentage. So I'll hand them back throughout the class and definitely during our break time. And then, right, there's also a large standard deviation to keep in mind. Let me double check the number. So yeah, 17.6 for your standard deviation. I mean, that's kind of what I expect for these exams. I wrote it purposely time intensive, so it was long. In general, though, I was pretty satisfied, honestly, with the grades. And then, right, if you're kind of on the lower end of the spectrum, no need to, like, panic, right? So that's my other thing, is, like, my goal is not to fail people in the class. But, again, if you're kind of on this lower end, then, you know, I can't say how grades will shake out, but I'm just kind of saying, right, maybe you're looking at a C. So I don't want people to, like, drop the class or think that they're failing, right? And so that being said, right, the ways to fail in this class are not taking the exam. So if you missed it, right, make it up ASAP. And I've talked to some people, so that's good. And then not turning in labs, right? So I don't mind if things are late, so just get things in ASAP. So turn in your assignments, and then don't forget your reading questions. So those reading questions online come back to haunt people, right? So I'm like trying to pass people, and then if people have none of their reading questions done, right, that's 10 points off of your grade right there. And I can only, like I said, I grade on the curve, but I can only curve so much, right? So you got to give me something to play with. So as long as you turn in all your assignments, I think you should be in kind of good shape. And yeah, so I don't want to get like too much into grades. So that being said, Blackboard is inaccurate. So I have no idea what Blackboard says for your grades, but so Blackboard is wildly inaccurate. So if it says that you have an A, that's probably not true. If it says you have an F, that's probably not true, right? So it's completely off, and I apologize. I've tried to fix it like last year, and then it like would not total up the calculations correct. So it's not worth my time, unfortunately, to fix it because it's so broken, and I can much more quickly do the Excel formulas. Like I can enter it in much faster than troubleshooting Blackboard, and that makes more sense. So that being said, right, refer to the syllabus. So that's what the syllabus is for. And you guys can calculate your grades. So I would refer to the syllabus, right? This gives the weighting of everything. So your exams are worth 45%. Like I said, I'm going to curve everything at the end, but I wouldn't depend on a curve. And so you can, again, kind of see how your grade is somewhat shaking out. So exams, 45%, and then, right, your labs are another big chunk. So most people do well on those, right? You just turn them in, fill them out, complete them, and usually people do really well. So use those labs as a buffer. So that's why, right, I combine your grades too on purpose for chemistry, right? So even though they're two separate courses, I'm going to average your lab and your exam grade to make one happy grade. All right, questions on grades and all that? So like I said, I don't want people panicking and crying and freaking out. But right, if you're on the lower end, just think about kind of what went wrong, how can you improve your study habits, right? Because it's an open note exam. So that's kind of the other thing. It's like there should have been no memorization issues on the exam. It's just an execution issue. So just think about how to improve better for next time, and we'll keep going forward. All right, let's warm up then. So how would we approach this problem? So we have the Coulombic energy of attraction between our lithium ion and our fluoride ion. So start with that calculation. And then you can also be thinking about this calculation. So maybe you don't have all the values you need, but that could be something that you start thinking about. What values do we need to look up to calculate that? What does it mean? What are the energetics involved? So I'll give y'all a minute or two to start that, and maybe I'll wait to hand out exams. All right, so let's hear how we're doing on this first part. So what formula do we have? What information do we need? And again, we might have a few small discrepancies depending on how you obtain this information. So let's start off. What's our formula? Do we remember the formula?
231 out of your per meter. And then Q1 times Q2 over distance.
Excellent. All right, so we have our formula. And so now we need to start just plugging in all of these. So what's my Q1 and Q2?
76 and 133.
Or, well, Q should be, yeah, 1 plus and 1 minus.
Oh, I'm sorry, yeah.
Yeah, you got excited there. No worries. Just so we're all on the same page. Okay, and then you said, sorry, do you have the distance?
The distance for lithium is 76, and then chlorine is 133.
So 133. So do people agree with those numbers? And again, right, you could have slight discrepancies. We should be looking at the chart over here. I think I have slightly different numbers. But it all depends where you get the numbers from. So I think it should be 136. Maybe I heard wrong.
I was looking at the chart in the book.
Oh, okay. What page?
183.
So 183. Let me pull that up because I do have the book pulled up as well. Because yeah, that's kind of the only tricky part. So yeah, you could get it from the book. So you're right, 76 and 133 is what it has numerically. I don't know why the chart is different. Again, right, I expect small discrepancies, so that's fine. That's why we show our work, and so we can follow along. And so then what do we get for our total distance? If we add these, or at least roughly, 209. And then, right, the other way that you could obtain this value that would be different is, let's say if we looked up lithium fluoride. And let's see what we can find, because it should say a radius. I don't know if Wikipedia is going to say it. So it gives our crystal structure. Let's just Google distance. I was trying to find the crystal structure data for this. I wish it would pull, oh, here we go. I don't like just pulling, right? There's nothing wrong with AI necessarily, right? Like AI is just pulling from different sources. So my only issue is like, okay, when it's telling us this random stuff, is like, where is it pulling from? That's disappointing. So the NIST is a good website. I don't know why it's not loading. Really? Because I just wanted to see it in a crystal structure, and usually the NIST is a good website for that. Yeah, and so this one is saying, again, we'd have to take a little bit more time to pull up a paper, but maybe in the crystal structure, right, it's saying like 201. So again, we might just find different numbers if we look it up. So expect there to be slight variances. All right, and then let's plug that in. Sorry, I don't have my calculator pulled up. And so now we can just plug all our numbers in. So 231 divided by 209 essentially. So then we should get about 1.1 attajoules or so. Is that what we got, right? Excellent. So that's our Coulombic attraction. And so negative 1.1, round it to 3 sig figs attajoules. All right, so questions about that process, just how to do that. Again, there will be discrepancies depending on where we get our numbers. And so now let's look at this one. And so this is another one we may have to do some book hunting to figure out. But before we start hunting around in the book or maybe asking Wikipedia or online, what are we trying to find? What are we trying to calculate again? What's going on in this process?
The energy release.
So energy release with what process? So you're kind of on the right track, but what? Because there's like two halves of an equation that we're putting together.
Bonding, by them bonding, forming like covalent bonds or ionic bonds.
So measuring, so kind of, but what was that measurement called? That I think you're kind of getting at. So we have, what did you say? Ionization energy? I thought someone said ionization. So, right, we have our ionization energy, but what is that linked to? What process is that? Which half of this? All right, so good. So, right, so ionization energy, right? Well, this is good. We're piecing it together. So that's essentially from, right, our metal giving up an electron. So yeah, that's this process. So lithium plus its ionization energy to give us our lithium cation and our 1 electron.
Plus the electron affinity of chlorine.
And then plus, so electron affinity, right? So going back to the other force that y'all were kind of dancing around. So then, right, electron affinity. And so we aren't measuring in a bond in this case, right? But again, just what does it take to add an electron to our metal? Electron to make our metal anion species. And again, plus electron affinity, right? So some energy. All right, so let's start combing through the book to find the energies of those processes, right? So these are just standard thermodynamic values. And let's see if I can figure out where they are in the book. So I think 107 should have ionization energies. And again, right, we may see slightly different values, and we also have to pay attention to what units we're in. So, right, these are given in attajoules, which is consistent with our Coulombic calculations at least. All right, so lithium, so first ionization energy, so looking at 0.86. 0.86, again, attajoules, right? And so now let's look up our electron affinity for fluorine here. So I think that's on page, thank you, 186. And so we have some electron affinities on the side. And again, all right, the book is giving it to us in attajoules. So fluorine has a negative 0.545 attajoules. And remember, right, that's showing us it's an exothermic process, so energetically favorable. So negative 0.545 for that process. All right, good. And so then, right, we could add these two reactions together and see our overall reaction. And really, we probably want to add in all of these. So now we'll kind of say our total energy of this process. And again, this is not giving us our full picture of, right, Coulombic stabilization. We're just kind of looking at 2 points, but for our purposes, that's good enough. So then we have negative 1.11 attajoules, right? And again, appreciating that this large electrostatic forces is what allows for that stabilization, because, right, we have this ionization energy that was endothermic, right? Endothermic, meaning that it needed energy. And we see that in our positive value. So again, just kind of putting everything together in your brain is we put energy into the system, right? We got some back out with this exothermic reaction. But again, if we just add those two numbers themselves, right? So 0.86 plus negative 0.545. So that gives us a positive value, meaning, right, energy had to be put into the system. But then our Coulombic process, so plus our negative 1.11, that shows us again where that energy of stabilization came from. So kind of our overall energy then is about, again, negative 0.795 attajoules for this process. So is that kind of making sense, putting everything together? So kind of looking at our half reactions here, and then again seeing that extra lattice energy stabilization piece. Questions? No questions? All right, so now we'll get into covalent bonding. And so covalent bonding, like we mentioned before, so now we have bonding pairs, or, right, we're sharing electrons here. And like we kind of went over yesterday with water, right, so we saw that water has these two lone pairs of electrons, right, that are not involved in bonding. And then it makes a covalent bond with hydrogen. And so we can see, right, so again, lone pairs, not involved in bonding. And then our covalent bond. Several ways to represent this, so I just drew it as two dots. And then obviously, right, we've also seen our single line convention. And so a little single line just means we have two electrons. And so your Lewis dot structure is again going to be pretty useful for this, and just kind of reiterating the information we've seen. So again, we have kind of two spots for bonding. So again, seeing that our group 6 likes to make two bonds, and then again our lone pairs are occupying this space, so that creates its geometry. All right, so now we can start to kind of explain the diatomics and why they are diatomics. So it doesn't tell us everything, but so if we look at hydrogen, so right, hydrogen, it exists as H2 in the elemental form since it wants to fulfill duet rule. And so we can see how they both kind of feel this bond. So I'm just kind of highlighting, right, to show that they're sharing these two electrons. So both hydrogens feel both of those two electrons, and again, they're both satisfied by the duet rule. So looking at fluorine, or the other halogens, right, pretty similar. So we can start with our Lewis dot structure, so 7 valence electrons. And again, right, we have one spot open, so that's telling you they tend to make one bond. And so that's true, so we see that again in our diatomics, or the halogen diatomics, so fluorine, chlorine, bromine, iodine. So they all have 7 valence electrons, and so they make 1 bond. I'll draw. And so again, just ways to analyze our structure. So I'm going to highlight, so this chlorine satisfied by the octet rule, it feels 1, 2, 3, 4, 5, 6, 7, 8. So it technically has 3 lone pairs on 1 chlorine. And so this one also has 3. Right, so all our lone pairs. And then again, right now we've only seen a single bond. So 2 electrons again in that bond. And I'll highlight the other one. So again, our chlorine feeling 8 electrons, so satisfied by the octet rule. All right, so try oxygen. So see if you can draw our structure of oxygen, so the Lewis dot structure of oxygen. So just kind of see if you can base it off of what we've been doing, right? Start with the Lewis dot structure of just regular oxygen. How many bonds does it make typically? So what do you think O2 will look like? And in making your structures too, so the other kind of hint I forgot to give is, right, count up how many valence electrons we have. So, right, we're just focusing on our valence electrons. We could base it off of our Lewis dot structure again, or again, this should also fall in line with our periodic table. So if we have 2 oxygens, right, each oxygen has 6 valence electrons, so times 2. And so this means, right, that we have 12 electrons to play with in our system to try to satisfy the octet rule. So what do your structures look like? What do we get? How many bonds?
2.
Yeah, 2, right? And so this is good. Again, see how powerful that is, right? We can know that this group 6 tends to make 2 bonds. And so just kind of playing with it. And so the other thing that I want you guys to kind of get comfortable with is, right, you got to get comfortable kind of experimenting and drawing and rewriting, right? You may not come up with this the first time. So this is what it should look like. Again, count your electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's always the first step, is you want to come to the party with the correct number of electrons, right? So if you're doing this on an exam and you have the wrong number, that's already kind of a bad start. And then the next thing we want to analyze is, okay, is the octet rule satisfied? And so let's kind of play with this another way, because again, I want you guys to feel comfortable like playing with it and exploring electrons, right? It's supposed to be a tool. And so let's just say you'd started off, typically it's good to put, right, a single bond between them. And let's just kind of play with it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, right, maybe you got to this structure initially, but then, again, kind of learning how to analyze these structures. Well, I'm looking at this, and this one this left-hand oxygen, right, is satisfied by the octet rule, 1, 2, 3, 4, 5, 6, 7, 8. But then this one is not, 1, 2, 3, 4, 5, 6. So that's not very good. So that right away is telling me that maybe we should move these over to a bonding scenario, which is again how we can arrive right back at here. So my point is we don't have to know the correct answer, right? We can kind of play with it. You can use what you know about these elements and atoms, right? And then kind of puzzle out the correct answer. And I mean, that's the really powerful thing about these Lewis dot structures and combining them. So excellent. So then, yes, just like you all predicted, we come up with our double bond now. So good. So double bond. So 4 electrons total, or 2 pairs of bonds. And then these double bonds, as we'll see, they tend to be stronger than a single bond, right? Since now there's more electron density between them, and also tend to be shorter. And again, that's just greater electron density, bringing them closer together. And so kind of as was implied in chapter 5, right, we're going to start kind of talking about things as a probability density map. So again, right, we're just saying that our probability density map between those is much darker, right, as we expect there to be a lot of electron density, especially with a double bond. And then we'll look into, again, we'll look at what orbitals are involved, but we'll kind of save that for second quarter. All right, so then do that for nitrogen now. So see if you can sketch out nitrogen, and again, predicting single, double, or maybe another type of bond. So how many electrons are in your party? It depends on the units. So, right, if you're looking at...
using 9 times 10 for decay. That was just nice. Instead of the 221 agile that you were using.
Oh, so you're in a different unit?
Yeah.
So yeah, if you're in kilojoules, then you just have to be consistent. But
okay, I was just because the one that you put for attajoules there,
yeah,
you put like 0.1, right, or some 0.11. But then for the whole reaction that has 1 mole, wouldn't we have to multiply by 6.022? That would got this number.
Well, like I said, it depends what you're doing, right?
Oh,
so
okay.
if you're looking at per mole, then it's a completely different, because I'm looking at like per molecule.
Oh, okay. Okay.
All right, so what do we get for nitrogen? So, right, starting off with our Lewis dot structure. So how many bonds does nitrogen want to make? So 3, right? So it has these 3 lone electrons, so it's ready for bonding. So it wants 3 bonds typically. And so how did you put your 2 nitrogens together to give you N2? So 2 dots on each nitrogen, and then we should end up with a triple bond then. So 6 electrons total, and then this is even going to be shorter and stronger. Again, just typically speaking, than a double bond. Again, right, that makes sense, just more electron density between them, and so that makes a strong bond there.
Is that why the first ionization energy connection is higher?
Well, that's just because that goes back to the atomic orbitals, right?
Okay, it's not
Yeah.
because it's diatomic.
No, because and when you do those calculations, like those are per an atom,
Oh,
so
okay.
not, yeah, for the diatomic species. Yeah, kind of confusing because, yeah, you have to remember how they're doing the calculation of just like usually a gas phase atom or like doing the experiment of a gas phase atom. Excellent. And again, right, just to kind of reiterate all the pieces. So nitrogen has 5 valence electrons, so times 2. So we have 10 electrons total. So just kind of double count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that looks good. And then again, just double check that everybody is satisfied by the octet rule. Right, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 there. So that looks pretty good for N2. And so just kind of continuing of what chemists want to accomplish and what we're trying to do too in research is how do we predict the type of bond. And so again, this is just kind of our general trend and what we've seen. So this is our electronegativity chart. And so we're given these values. And so like we mentioned, so fluorine is the most electronegative. So this mainly has to deal with, right, our effective nuclear charge as we continue to fill in this 2p orbital, right, that's really close to our nucleus. And then we have our other values here. And again, kind of our lowest are francium and cesium on our chart. And then kind of in general, so right, we have our types of bonding. And so we can have a pure covalent bond. Nonpolar is another way to refer to it. So electrons are shared equally. And so this could be like, let's take fluorine, right? So fluorine, even though fluorine itself is extremely electronegative, right? If it's in a compound with itself, well, what's the electronegativity difference between them? None, right? So 0, so obviously that's going to be perfectly covalent, and then that just means, right, when you draw out their little atomic orbitals, their electrostatic potential map, right, is all nice and even there. And so then once we get into our polar covalent bond, let's see what this means. Again, right, this is just kind of a guide. That's why I always say, right, this is what chemists are interested in. It's like actually crystallizing compounds, measuring the bond length, right, seeing if that's typical or atypical of that bond, and then trying to figure out, right, what's going on, looking at MO calculations, trying to figure out how many electrons are actually occupying those orbitals. But again, this is a good guide. And so let's just practice with HCl. So now a polar covalent molecule. And so we can just double check that. So again, I would provide you these values on an exam. And then we can take our difference. So chlorine is 3.16 minus hydrogen, so 2.1. And so that gives us a difference of 1.6. So that difference, right, falls right into the range of intermediate, where we have, again, a polar covalent bond. And so all that means, so we'll have our HCl here, and our electron cloud is going to be more polarized, aka larger, around our more electronegative element there. So again, just kind of showing how chlorine is taking that electron density, leaving hydrogen with this partial positive. Again, pretty similar to water, right? That's how we get That's why water is so polar, and again, going back to why water can adheres to everything, and right, it adheres to itself, so all those properties. And then once we get a large separation, again, typical of an ionic compound, metal plus a nonmetal, but let's just see this numerically now with sodium chloride. So I'll plug in chlorine again, so 3.16 minus our sodium, so 0.93. And so that gives us, right, 2.23, and so that is over the difference of 2, like they say. And so again, that's why we expect the ionic bond there. So this is just a general guideline. So you just want to be familiar with kind of the differences between them and be able to calculate them. All right, so then continuing, so like we went over, we had our single covalent bond. And so, right, anytime you're trying to make a compound and put it together, right, just start with your single bonds. And any single line just represents 2 electrons, just like we saw here. And then again, just a reminder that hydrogen follows our duet rule, so only makes 1 bond typically. And then we saw oxygen with our double covalent bond or double bond, so again sharing 2 pairs of electrons, or 4 electrons total. And then just kind of, this is half trivia, half just kind of preparing us for the future, right? So just kind of typically speaking, elements that can double bond are carbon, nitrogen, oxygen, sulfur, phosphorus, and just kind of thinking about where you're going to see them. So, right, these are organic molecules typically, right? Just start thinking of drug development as well. That's where you typically get these sorts of functional groups. And again, that's where you're going to be seeing in double, triple bonding scenario with different organic compounds. So just kind of be aware. And then we have a triple bond. And again, sharing 6 electrons. And so nitrogen is our typical example of this. And then carbon can also do triple bonds. And then you could get kind of weird scenarios with like oxygen and sulfur kind of doing this bridging temporary bonds, but we'll get there when we get there. All right, we're kind of, let's keep going just a little bit. So let's just try OF2 for a second. See if you could come up with a structure. So how's our structure looking? So again, first thing you probably want to do is see how many electrons you're bringing to the party. So oxygen has 6, fluorine has 7, and then there's 2 of them. So it looks like, right, we have 20 electrons to kind of play with. And I think this one kind of works out pretty nicely to just start kind of putting bonds to it, right? And then we know that fluorine already came with 3 pairs of lone pairs each, so kind of see where you're at. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And so that does, right, work out pretty well. And then that should be kind of what we expect, right? Again, oxygen typically makes 2 bonds, and then our halogen typically makes 1. So that kind of makes sense, right? And it should kind of remind us of water. So just see, right, the similarities in those structures. So that's the other thing that you want to get used to is, right, to start seeing all these repeated patterns of how these molecules tend to typically react. And then I wanted to hand out a sheet. It didn't print quite right, so I'll go reprint it while you work on your quiz, but let me pull it up on here. So we can start kind of looking at it. This is more chapter 10, but I think it's helpful to kind of start looking at the geometry as we make it. So, like I said, I'll reprint this sheet for you guys. And so it's this PDF, although you may want to just look at the color one directly. And so it has this key on the side. And so this key starts with these numbers. So basically how many things are attached to it. So it calls it electron pairs. But let's kind of go through how to use it. So if we're looking at oxygen, right, it has 2 lone pairs. Let me write this out. So 2 lone pairs, and then it's attached to 2 atoms, right? So it has kind of 4 things total on it. So that means that it's in the 4 electron group. And then if this had been like a double bond or triple bond, it doesn't matter. It's just like how many things are attached to it. Okay, so then we go down to our key. So that means we're in the 4 electron pair group right now. And then the other thing that you want to kind of start looking at is how all the different geometries are related. So we start with tetrahedral, right? And then you should right away think of methane. I forgot my molecule kit. So, right, we have methane, okay, right? Carbon in the middle, 4 hydrogens, typical structure, right? Tetrahedral geometry, so you're kind of seeing that. So that's with 4 bonding pairs. And then, right, eventually we'll look at ammonia. So that's going to be our trigonal pyramidal typical compound, where we've removed 1 bonding pair and replaced it with a lone pair. So now I'm just kind of, I want you guys to be visually, right, thinking this in your mind. So, okay, ammonia, same structure, right? So same tetrahedral structure. It's just now we have a lone pair giving us this like trigonal pyramidal geometry. And you can kind of see the pyramid, right? And then, okay, so this is the one we're actually currently looking at. So bent, so like we said, okay, 2 bonding pairs and 2 lone pairs. And again, right, you're just appreciating, yes, that is why water has that shape. That's also why OF2 has that shape. And, oops, I didn't mean to close that. But then, right, you can always look it up and kind of verify it. So looking at water, yeah, excellent. It's got that bent structure from those lone pairs, and you want to be thinking about that space that the lone pairs are occupying, right? Because again, chemistry occurs in 3D. Like, I can't say that enough. Like that's the hardest part about OChem is that you have to think about everything in 3D. So it's best to like put yourself thinking about the 3D nature of molecules right from the beginning. So you're thinking about these lone pairs hanging out. And then, right, just we'll put oxygen, fluoride. Again, just so we can appreciate, yes, it is bent, right? And then, of course, we could get into the slight differences in its geometry. You can kind of see, right, slight deviations just based off of the size and the nature of their single bond. But again, just appreciating that they're bent, kind of putting everything kind of together, right? So we're just trying to put all the layers together with chemistry. And let's go over this. So we'll kind of end on this note just in case this comes up on the homework. So this goes back to analyzing our structure. And let's do the oddity. Let's do an oddity. So play around for a second with CO and see what you get for its Lewis dot structure. So how many electrons you have in the party? And then question for the chat. Yeah, it's a 200 level chem course.
We're not allowed to add another atom, right?
So let's start hearing your thoughts. So most important thing to start with is, again, how many electrons we have total in our system. So we have 4 from carbon, 6 from oxygen. Okay, so we have 10 electrons to play with. So let's just hear your structures. What do we have so far? Remember, there's no like right or wrong answers right now. We're just trying to figure out how to analyze our structure.
Well, carbon wants to make 4 bonds, right? Like, there's an electron on each side.
Yeah, typically.
And oxygen wants to make 2 bonds.
Yeah.
So that's where I got stuck. I was like,
I mean, you could just
how do
kind
you
of
make carbon
start.
happy?
Yeah, I mean, well, that's why I gave you this problem is, yeah, how do we make everybody happy? And then what does this mean when we fully analyze it? So, okay, you're kind of telling me to start with 2 bonds here and then 10 electrons. So 1, 2, 3, 4. So how should I put the other 6?
Carbon would get 2 and oxygen would get 4 in that case.
All right, so let's see what we think about this structure. So again, right, this is just how we analyze our structures and how to approach this. So 1, 2, 3, 4. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we have the correct number of electrons. So again, on an exam, I'm not going to fault you for that. But then we want to see, so let me do that, right? Is our total electron correct? So, okay, check. And now we want to look at, so what about the octet rule, right? Is that satisfied or not? So is our octet rule satisfied for carbon? So how many electrons does it feel? So 6. So maybe not the best structure, right? So I'm just going to put that carbon feels 6 electrons. Again, right? We're not trying to be wrong or right. We're just kind of seeing where could the electrons be? What makes sense? Okay, oxygen's satisfied by the octet rule. Okay. And then there's one piece that I haven't taught y'all yet. The other way to analyze our structure and what we're going to need is this formal charge. And so let's go over how to calculate it. So this is the formula. And then sometimes I slightly modify it, I say. So this, right, formal charge on an atom in a Lewis structure. So this is, right, what our formal charge is. So this is equal to, so we start with the number of valence electrons in our free atom. And so, right, again, you're just thinking valence electrons from periodic table. That's all that means. So let's do this analysis. So we'll start with carbon. And so for us, oops, sorry, scrolling wildly. So carbon, so okay, we start with 4 valence electrons, right? That's just from the periodic table. And then it says, then we subtract the total number of lone pair electrons. And so I like to think of this as minus the individual electrons. And if I could spell. Individual electrons. So, right, sometimes it won't happen often, but it may happen where we have a radical, right, so an odd number of electrons. So that's why I say count each individual electron. And so in this case, right, it's 2, so minus 2 electrons. And then they use the term minus half the total number of shared electrons. And so for them, right, we're sharing 4 electrons, so 4 divided by 2 is 2. The way I like to think about it is minus the number of bonds. So they should give you the same result. And so again, for carbon, minus 2 bonds. Okay, so this is looking good so far. So I have a formal charge of 0. Okay. And then let's try that for oxygen now. So oxygen, 6 valence electrons, right? Minus 1, 2, 3, 4 individual electrons, minus 1, 2 bonds. And so that gives us 0 as well. And so kind of the caveat with formal charges and what we're trying to figure out is, again, it does tell us some information, like where electron density could be located. But it also can tell us, right, is the structure kind of good or bad? And so typically speaking, we want to minimize formal charges. And so the confusing thing about this scenario is, right, well, we're violating the octet rule, but right now our formal charges are pretty happy. But what could we do to maybe satisfy the octet rule? And I would think about trying to move these electrons as a pair. So that's typically the best way to move electrons. So what could we do?
For the middle.
So let's put them in the middle. Let's try to make a triple bond, and let's see what that does. So now we have our triple bond. So 6, 7, 8, 9, 10. So again, right, we want to have the correct number of electrons. That's always important. Now let's check our octet rule. Okay, 1, 2, 3, 4, 5, 6, 7, 8. I'm feeling good about that. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now they're both satisfied by the octet rule. But let's look at our formal charges. And so what do we get for the formal charge of carbon. So walk through it with me. So how many valence electrons does carbon have? Yeah, 4. I see your finger. So 4, and then minus. So in our new structure, so how many individual electrons does it have? 2. So minus 2. And then how many bonds? So 3. So minus 3. So that's -1. And so let's try that for oxygen. So how many valence electrons does oxygen have? 6. And then how many electrons does it have in this structure? 2. And then how many bonds? So 3. So we get a 1+. And so this is kind of an issue in some ways. And so, right, kind of the next step with the formal charges is, well, not only do we want to minimize them, but typically we want the negative charge on the most electronegative atom. And so right now that's not the case for CO. And I mean, this could honestly be a little distressing, right, unless we have outside information, because how do we kind of reconcile these two structures? But that being said, right, so this is a good analysis. And then this tells us something kind of further. So yes, this is super strange that the negative charge is on the carbon, right? So we would not expect this typically. But it does hint at the reactivity. And so what we find, and for some reason I just got nickel carbonyl on the brain, even though, so you wouldn't actually want to use nickel carbonyl, nickel tetracarbonyl. It's fun because it's one of those, it's a liquid, right? But it's such a heavy liquid that most standard fume hoods are not capable of like sucking it up and providing right enough flow to be able to work with nickel tetracarbonyl safely. And then it's a toxic substance. And then I'm trying to draw it in 3D there to show that it also does this 3D tetrahedral geometry. But again, so what this implies, so with our negative charge being on the carbon, what we find is that, yes, this is actually indicative of CO's reactivity. And so if we see how CO binds to metals, it binds at the carbon to any metal species. So again, right, those electrons are coming from the carbon then in its orbital and donating to the nickel. So a lot of information in there. And so again, kind of, right, recap takeaways, what's important. So, right, we want to, again, bring the correct total number of electrons to the party. That's like the most important thing, right? We have to start with the correct number of electrons. And then from there, it's just how can we best satisfy the octet rule? And then how can we best, right, minimize these formal charges? And then that being said, right, on an exam, if I were just like, oh, what's the Lewis dot structure of CO? I would accept both of these as kind of correct answers, right? The important thing is, did you do the analysis? So if you show this structure, right, you want to point out that, yes, it's deficient in electrons, so maybe that's not best, but, right, you're pointing out that the formal charges are 0, so that's good. And then if you had selected this one, again, same thing, you want to point out that at least you've satisfied the octet rules, and then you can point out this is a little strange. And if we didn't have this knowledge about the reactivity, right, we would just be like, well, that's kind of strange, and kind of, you know, see what you can do with that information. And that, right, you could try to draw a different structure that puts the formal charge on the oxygen, but of course, if you were to play around with that, you'd see you get crazy structures. So this is truly the best representation of CO and its reactivity. But like I said, unless you know that the carbon attaches at the nickel or at any metal, then that may not be so obvious why this is the case. But a lot of information that you can glean from that. All right, I'll stop talking for now. All right, so I'll get printouts. So I don't know what happened to the polyatomic chart I printed it didn't make it to the printer, so I gotta reprint that, and I'll reprint the compound chart. And so like I hinted at the beginning of class, I wanted to do a quiz, but I wanted to kind of make sure we're all on the same page from the quantum chapter material. So I have kind of our quiz, but we're going to make it a group quiz. And so if you guys want to turn in like a group quiz, so like, if you have a group of 4 and you all kind of work together, you can just turn in one quiz, just put all your names on it. If you don't trust your group and you just want to turn in your individual effort, you're more than welcome to do that as well. I'm trying to think if there's anything else you say. And then, you have obviously the rest of the period to work on the quizzes. If you need to take it home, you can. I mean, I'm not anticipating that it would take that long, but just throwing that out there. Oh. Yeah, because that's the whole point. If you do it now, that's how it's
This is my last one.
Yeah, so you have like 1, 2, then I skip these, and then you go back to the summer, 3, 4, 5, 6, 7, 8. So that's like the easiest way.
Do a group.
Alright, did everybody get a quiz? And then of course take your break if you need it. And then I'm going to leave extra copies of the quiz up here, so if you want to do, like I said, a group submission, feel free to do that. And then try to limit the groups to 4 or 5, max. Obviously I don't want one class group quiz, but or
Or I guess we can just not.
I have no idea what I'm doing.
Okay, I think the quiz is missing a page. So I'm going to, this is like epic failure day. I gotta reprint your quiz. That was it didn't go 2-sided. My bad. Alright, so.
Congrats on the review.
You guys too.
Wait, so it's just like all activities. As you're hosting it,
Yeah.
how many games would that be if you go out?
Because that's.
You did 16 games. Like the brackets.
Yeah.
So do you have first round bye? So probably the next big quarter.
I think so. I think last year we had 2 games per day for the weekend. But we didn't make it. And then we go off to the Elite 8.
Wait, really? Wait, it's
I think so. I honestly don't know this, but that's how it is.
So is the finals? Where's the finals at?
To win the whole NY? Not sure, it depends on where the place is. Yeah.
Oh.
Yeah.
Wait, so what is this tournament?
This tournament is, so we have our playoffs, and then obviously if we win, then we go off to the Elite Eight. And we continue to win all the, yeah.
So this is to go to the Elite Eight, is it?
Mm-hmm.
It was just a 5.
I don't think it's 25, 10 or 50.
Yeah, we got one.
Did you know that there's theoretical G and
Maybe
H orbital?
That's really cool. What does that mean?
I remember what it means that there may be elements who can contain more electrons in their shells than we originally thought. Theoretically speaking.
Yeah. You didn't really get into it.
Yeah,
Basically.
it's the legal test for like a little program.
I mean, that was what he said was basically there was some questions on it. So here's the question.
I don't have anything about Schrodinger in my notes. Nothing.
That's the 30.
I did my damnedest to understand that statement, if not. It's 5S, 5Q, 5Q.
And the electrons is 2. This is something.
Like, it took us like 30 minutes to like, do something on the tape. So we're there for like
Sorry, I'm gonna hand out your actual quiz without missing pages. Yeah. At least it's green, so. I apologize.
Oh, you're taking, what was it, copper? You're just like melting copper and then you create
It was so warm.
Sorry, here's your replacement quiz. Entire quiz.
Uh-oh.
And then try to start with your neighbors for help, but you can phone a teacher if you guys get really stuck.
We need an extra one.
Oh.
No, 'cause in the lab,
That too.
in the lab, you just have to go like, Dr. Shepard. Like, oh,
We got an
Oh, you need a
Actually, really.
Everyone in the
Anybody else not get to
Oh, yeah.
actual quiz?
Those, it's really easy to make that.
What?
Sorry.
You make LSD. That was a real conversation.
And then I'll leave, like I said, a stack of extras if you want to do a group effort
Because all
quiz.
drugs are easy to make if you know what to do.
Just gotta watch Breaking Bad.
Yeah, I was gonna say, the only thing that bothers me about Breaking Bad is that his super pure meth is like blue.
Yeah, what's a
What
policy?
color is it supposed to be?
White.
Uh,
Like, unless